In this episode, we turn our attention to one of the most damaging outcomes of a cloud compromise: data exfiltration. After gaining access and possibly moving laterally, attackers often aim to extract sensitive information, whether that is customer records, intellectual property, credentials, or internal documents. Data exfiltration can be noisy, but sophisticated attackers try to make it look like normal traffic, which is why detection requires careful observation rather than simple rules. The cloud makes exfiltration both easier and more complex because resources are globally accessible and services frequently communicate with external systems. That means you cannot assume all outbound traffic is suspicious, but you also cannot ignore it. By the end of this discussion, you should understand how volume baselines, destination analysis, and timing patterns work together to reveal attempts to move data out of your environment without authorization. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Data exfiltration simply means transferring data from a trusted environment to an external location in a way that violates policy or expectation. In the cloud, this can happen through many legitimate mechanisms, such as copying objects to external storage, sending large responses over encrypted connections, or synchronizing data with third-party services. Attackers do not always need specialized tools. They can use built-in cloud APIs, standard protocols, and normal user privileges to retrieve and transmit data. This is why traditional malware-based detection may not be enough. Instead of focusing on malicious code, you focus on patterns of data movement that do not align with business needs. Exfiltration detection is therefore about understanding how much data normally moves, where it normally goes, and when it normally moves. Volume baselines are one of the strongest starting points because large-scale data movement often stands out against normal patterns. Every workload and service has typical data transfer characteristics, such as average outbound bytes per hour or typical response sizes. By observing these metrics over time, you can establish a sense of what is normal for each resource. If a database server that usually sends small query responses suddenly begins transmitting gigabytes of data externally, that is a meaningful change. Even smaller deviations can be significant if they involve sensitive systems. Volume baselines are especially useful because they do not depend on inspecting content. They rely on measurable patterns that are hard to disguise completely. Attackers can try to limit transfer size, but they often need to move enough data to make their effort worthwhile. Destination analysis complements volume baselines by focusing on where data is going rather than how much is moving. Not all external destinations are equal in risk. For example, connections to approved business partners or well-known service providers may be expected, while connections to newly registered domains or unfamiliar IP addresses may not. Destination analysis involves maintaining awareness of which external endpoints are approved and monitoring for connections outside that set. It also includes watching for first-time connections from sensitive workloads to external systems. Even if the volume is not huge, a sensitive database contacting an unknown external host is noteworthy. Attackers often use infrastructure they control, which may be newly created or rarely seen in your environment, making novelty itself a valuable signal. Timing patterns add another dimension because attackers frequently operate outside normal usage windows. If large outbound transfers occur late at night, during weekends, or at times when the associated users are inactive, that can indicate unauthorized activity. However, cloud systems often operate around the clock, so timing analysis should consider workload-specific schedules rather than human office hours alone. For example, a batch processing job may legitimately send data at midnight every day, but a sudden mid-afternoon surge from the same system may be unusual. Timing also matters in relation to other events, such as suspicious logins or privilege escalations. If an identity is compromised and within minutes large outbound transfers begin, that temporal proximity strengthens the case for exfiltration. By correlating timing with identity and volume signals, you move from vague suspicion to structured evidence. Another important signal involves data egress pathways that bypass expected controls. In cloud environments, there are often defined paths for external communication, such as approved gateways or managed integration points. If data leaves through an unexpected route, that may indicate policy circumvention. Monitoring should therefore include checks for direct outbound connections from systems that are supposed to communicate only through controlled channels. Attackers may attempt to exploit overly permissive network rules to send data directly to external storage services or remote hosts. Identifying traffic that bypasses approved egress points helps expose these attempts. Strong architectural design makes this easier by limiting where outbound connections are allowed in the first place. Encryption complicates exfiltration detection because most legitimate cloud traffic is encrypted. You cannot rely on reading content to identify stolen data, and in many cases you should not attempt to inspect it. Instead, focus on metadata such as byte counts, connection frequency, and destination characteristics. For example, a sudden increase in outbound encrypted traffic to a rare destination can be suspicious even if you cannot see the content. Patterns like repeated small uploads to the same unfamiliar endpoint may indicate staged exfiltration designed to avoid volume-based alerts. Monitoring encrypted traffic therefore requires careful analysis of behavior rather than payload inspection. The goal is to identify anomalies in communication patterns that suggest data transfer beyond normal business use. Cloud storage services also play a central role in exfiltration scenarios. Attackers may copy objects from one storage location to another within the same provider, especially if they can access cross-account features. Monitoring for object copy events, bulk downloads, or replication configuration changes can reveal attempts to move data silently. Storage access logs often include information about which identity accessed which object and how much data was transferred. Unusual spikes in read operations against sensitive buckets or databases can indicate preparation for exfiltration. If those read operations are followed by outbound traffic to new destinations, the correlation becomes even stronger. Combining storage logs with network flow data provides visibility into both the access and the transfer stages of exfiltration. Volume analysis should also consider gradual exfiltration, not just sudden spikes. Some attackers move data slowly over time to stay under detection thresholds. In these cases, cumulative analysis becomes important, tracking total outbound volume over days or weeks rather than hours. A small but persistent increase in outbound data from a sensitive system may be easier to detect when viewed in aggregate. Similarly, repeated access to high-value records over extended periods can indicate systematic extraction. Baselines must therefore account for both short-term and long-term patterns. Detection logic should be flexible enough to catch both bursty transfers and slow drips. False positives can occur when legitimate business activities generate large or unusual transfers, such as backups, migrations, or analytics exports. To reduce noise, monitoring should incorporate contextual information about planned events and approved workflows. If a data migration was scheduled and documented, a temporary surge in outbound traffic may be expected. However, if similar surges occur without corresponding change records, investigation is warranted. Contextual awareness improves accuracy by distinguishing between authorized and unauthorized behavior. The aim is not to prevent all data movement, but to ensure that sensitive data moves only through approved and visible processes. Clear communication between security and operations teams supports this effort. Investigation of suspected exfiltration requires a structured approach that traces the sequence of events. Start by identifying the source system and the identity associated with the outbound transfer. Then examine whether there were unusual login events, privilege changes, or lateral movement leading up to the transfer. Review destination details to determine whether the endpoint is known and approved. Examine volume patterns to assess whether the transfer aligns with normal behavior. This step-by-step review connects exfiltration signals to broader compromise indicators. Effective investigation depends on having retained sufficient logs and metadata to reconstruct the timeline. Ultimately, detecting data exfiltration in the cloud relies on observing changes in how much data moves, where it goes, and when it moves. Volume baselines highlight unusual transfer sizes. Destination analysis reveals unfamiliar or unauthorized endpoints. and timing patterns expose activity that does not align with expected workflows. Correlation with identity and lateral movement signals strengthens confidence in detection. By focusing on metadata and relationships rather than content inspection, you maintain visibility even in heavily encrypted environments. Exfiltration is often the final stage of an attack, but early detection can prevent significant loss. Understanding these principles prepares you to refine detection systems so they reduce noise while still capturing high-confidence alerts, which is essential for maintaining effective cloud security monitoring.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.